FlashAttention fundamentally changes how we handle attention mechanisms. By avoiding the creation of a large n-by-n score matrix, it significantly speeds up processing. This approach is crucial for real-time applications that demand fast computations. FlashAttention takes a novel approach by computing attention in smaller, manageable blocks. This method keeps the computations within fast on-chip memory. It leads to quicker processing and reduces the need for slower off-chip memory access. Traditionally, attention mechanisms require a large n-by-n score matrix, which is computationally expensive. FlashAttention circumvents this by processing in smaller submatrices. This reduces memory footprint and enhances speed without sacrificing accuracy. In this episode, we'll explore how FlashAttention optimizes computation through tiling and online softmax. By understanding this mechanism, you'll see why it's a game-changer for neural networks. Attention mechanisms allow neural networks to focus on relevant parts of input data. They compute score matrices that determine the importance of each element. In a sequence of 512 tokens, this requires extensive computation, influencing model performance. Traditional attention computes an n-by-n score matrix, where n is the sequence length. For a sequence of 512, this results in over 260,000 elements. This computation is memory-intensive and impacts speed. Calculating large score matrices demands significant memory resources. Each element in the matrix needs to be stored and processed, increasing memory usage exponentially. This limits scalability and affects real-time applications. FlashAttention revolutionizes traditional methods by computing attention in SRAM blocks. This innovation avoids creating the full n-by-n matrix in HBM, drastically reducing memory demands and improving processing speed. FlashAttention breaks the input data into smaller tiles. This approach allows computations to be performed in the faster SRAM rather than the slower HBM. By processing these smaller tiles, memory access is optimized, leading to improved speed and efficiency. Online softmax computation processes data progressively within tiles. Instead of storing large intermediate results, it computes softmax on the fly. This reduces memory usage and eliminates the need to store the entire n-by-n score matrix. Materializing the n-by-n score matrix would require significant memory bandwidth. FlashAttention avoids this by performing calculations directly in SRAM. This not only speeds up computation, but also reduces memory bottlenecks. Being I/O-aware focuses resource use on efficient data movement. FlashAttention prioritizes memory access patterns over raw computation. This leads to faster processing times as it optimizes data transfers within the hardware. FlashAttention optimizes memory use by avoiding the full n times n attention score matrix. This is achieved by computing attention in smaller SRAM blocks. Consequently, memory bandwidth demands decrease significantly, enabling faster processing. The tiling technique divides tasks into smaller blocks processed in SRAM. This design reduces the need to access the high-bandwidth memory. As a result, it cuts down on data transfer, improving speed and efficiency. By reducing memory traffic, FlashAttention lowers bandwidth demands. It achieves over a 50% reduction in memory usage. This results in faster attention computation, especially beneficial for longer context sequences. While FlashAttention speeds up computation, it may involve more complex coding strategies. Developers must balance between performance gains and the complexity introduced by this approach. However, efficiency gains often justify the complexity. Let's walk through a basic implementation of FlashAttention. We focus on arranging computations into tiles. This enables efficient use of on-chip SRAM and prevents memory bottlenecks. FlashAttention requires a specific CUDA version to function correctly. Ensure your environment is compatible. For instance, it may need CUDA 11.2 or higher. Using an unsupported version leads to errors. Enabling FlashAttention on incompatible GPUs is a common mistake. Only certain GPUs can efficiently handle its I/O-aware operations. A wrong choice can degrade performance significantly. With FlashAttention, we compute softmax online using SRAM blocks. This avoids creating large n-by-n matrices in high-bandwidth memory. The trade-off favors reduced I/O operations over raw flop efficiency. The first step is verifying your GPU supports FlashAttention. Look for modern architectures like NVIDIA's Ampere or newer. This ensures your hardware can optimize attention operations efficiently. Without compatibility, you cannot leverage the speed benefits. You'll need specific libraries to enable FlashAttention. Install PyTorch or TensorFlow with the latest updates. These frameworks have built-in support for optimized attention mechanisms. They connect directly to your GPU for enhanced speed. Next, Configure your model to use FlashAttention. You'll likely modify settings in your model definition to enable this feature. This step ensures your code communicates correctly with your GPU. Finally, test the performance improvements. Run benchmarks comparing execution times before and after enabling FlashAttention. Expect reductions in processing time, sometimes by up to 50%, depending on the model size.